All right, and we're here to pick up with just the very last bits of our acid-base chapter, talking about leveling effects and solvating effects. And so when we talk about a leveling effect, what we're really doing is we want to give ourselves some basis for picking a solvent for an acid-base reaction. So this is an important criteria for organic reactions. So when we actually do organic chemistry, one of the key choices is what solvent will we use? And the key is that the solvent should be able to facilitate reactants hitting one another or catalysts hitting one another. But the solvent itself can't react with those catalyst molecules or with the reactants. So in an acid-base reaction, we have to consider, is our solvent gonna react as a base? Is it gonna react as an acid? And water can do both of those, right? We know that water acts both as an acid and a base. And overall, it has a leveling effect. So this is just one example, is using water, something that we're familiar with. If we have an acid that's stronger than the hydronium ion, we can't use that acid in water. If we do, we add the acid to water, it immediately donates as a proton to hydronium ion, meaning the only acid that we have around is the hydronium ion. So our stronger acid is no longer stronger. It's just been all absorbed by the water to form the hydronium ion. Same as with bases that are stronger than hydroxide. So if we have a really strong base, like NH2-, for example, we put it into water expecting it to do a reaction. What actually ends up happening is that NH2- deprotonates water and forms the hydroxide ion. And so we don't have our strong base anymore. It's actually reacted with the solvent. So that's what we call the leveling effect. So like here, for example, let's say that we have acetate. We want to use acetate in water. And the way that we can figure out whether it's appropriate or not is, let's say that we use acetate in water. Let's just draw the imaginary acid-base reaction, the proton transfer from water to acetate. So when we do that, the acetate lone pair picks up a proton from water, forming the hydroxide ion. So this is our proton transfer reaction that forms acetic acid and hydroxide. Well, now let's take a look at the position of equilibrium. pKa of acetic acid is 4.75. The pKa for water is 16. So we know at equilibrium, we're going to favor pretty heavily the acetate water side of equilibrium. That means acetate can be used. Now we could easily imagine a case where we have a pKa greater than 16, so we would have the products favored. In that case, it would not be appropriate to use that base in water. So yeah, so for example, another example of an acid that can't be used in water. So like if you look at sulfuric acid reacts with water to form the hydronium ion. So if you try to use sulfuric acid in water as your strong acid, well, sulfuric acid is going to give up its proton to water, and what you're going to end up with is hydrogen sulfate and the hydronium ion. And the pKa of sulfuric acid is -9. pKa of the hydronium ion is -1.7. So if you need this -9 pKa, well, the water is going to neutralize it. It's going to level that pKa all the way down to -1.7. So just keep that in mind, that we're not going to have any sulfuric acid around when we want to have that as our strong acid reagent. Similarly, if you have a base that's stronger than hydroxide, you can't use that in water. I already mentioned an N-. So this is a kind of an ammonia anion. Here, if we're going to do this reaction where we deprotonate this terminal alkyne, this lone pair has to pick up this proton here. If we were to do this reaction in water, what would happen instead is this nitrogen would be protonated by H2O, forming hydroxide ion. And the hydroxide ion is not strong enough to actually pick up this proton from this alkyne. So this reaction wouldn't be able to occur because this base is too strong. I hope that makes sense. That's what we call a leveling effect. It means it takes your strong base and turns it into our OH-, which is not as strong of a base. So what do you think, what solvent would be a good choice for that? So come up with a good solvent for that. One could be, for example, ammonia itself. All right. So that brings us to sample exercise number 9. And this is the question: which of the following solvents could be used with NH2-? So the way you want to answer this question is, go ahead, draw a a proton transfer reaction involving the solvents that we've listed here, so ethanol, pentane, water, and ammonia. Draw that, and then figure out which position of equilibrium is going to be favored. Is it going to be the products or that contains the leveled base, or is it going to be the reactants that contains our NH2 minus, which is what we want to use? So go ahead and do that. We'll do that together on the sample exercise video, but you can pause the video here and try to come up with your answers now. Okay, just a couple last little points here from this chapter, and then we'll be done. We have the solvating effects first up. So REO is really good when we have two protons that are on really different molecules, but sometimes we actually have things that we can't explain using just the REO method. For example, we have tert-butanol and ethanol. So we've talked about T-butanol a lot actually this chapter because it's very useful in certain regards. And if we look at the pK of tert-butanol versus ethanol, it's not something that we could explain by using the REO method. Both are on the same atom, they have the same amount of resonance, they have the same inductive effects, and they have the same orbital. So nothing from REO really explains what we see when we see a pK of 18 for tert-butanol and a pK of 16 for ethanol. You predict they have this essentially the same pKa. So what we actually have to do to explain it is we actually have to look at the conjugate base, and in particular, we want to look at the ability of a solvent to stabilize the conjugate base. So again, this tert-butanol is going to become tert-butoxide. This ethanol becomes ethoxide. So when we look at the difference here, what we actually find is that tert-butanol, because it has an extra carbon in its backbone, that actually takes up a greater amount of space. It's what we call a steric effect. This is a sterically hindered conjugate base. And because of the sterics of this, the size of it, there's not as many solvent molecules can get around and get close to the negative charge on the oxygen atom. When you compare that to ethoxide, it's lacking two of the what we call methyl groups on this side, so two separate carbons are gone. And so there's another place where solvents can kind of get closer and actually stabilize the negative charge on the oxygen by using their partial positive charges. So because of that, T-butanol's conjugate base is less stable, and so T-butanol itself is less acidic. Okay, last little bit here. One thing that we're going to see a lot in organic chemistry is what we call counterions. This is something that we worried a lot about in general chemistry. That's why we bring it up now. Just don't worry about counterions. So here, what we have is like we have NaNH2. We have a sodium counterion with NH2 minus as the anion. And reacting with water, that forms ammonia and then sodium hydroxide. Now, if you stick the sodium in here, it balances the charges nicely, but the sodium doesn't really do anything. It doesn't pick up any electrons, doesn't give away any electrons, so it's not really involved in the reaction. So most of the time, we're not going to include counterions at all. We're just going to write NH2 minus plus H2O, and that forms NH3 and OH minus. So just get used to like not involving the counterions at all. And in fact, when I write the counterions on the test, you can like cross them out. Don't draw electrons pointing at the sodium. That's for sure going to get you the wrong answer on the test. So just keep that in mind. We're getting back to kind of the days when you had to do net ionic equations, if you remember those, where you cross out the spectator ions. You can just ignore those sodiums. So, and now I believe that concludes our chapter. So go ahead, move on to the sample exercise video. Make sure you got your sample exercises correct, and then you can start the homework. And go ahead. If you have any questions, make sure ask them down in the discussion here, and I'll be paying attention to that discussion as you have those questions. So I'll see you soon. Bye-bye.